In last session, we learned about the 2-bit asynchronous counter design, how to design that. Now in our session, so let me design your 3-bit triple counter. So now, so in last session, because of that 2-bit, so we used only 2 flip-flop. Here to design a 3-bit triple counter, we need to prefer 3 flip-flops as each flip-flop is holding 1 bit of data. So the number of states available from that counter of 3-bit is 8 states. So it is started with 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0 and 1, 1, 1. So now number of states depends on your number of flip-flops which are going to use in your counter. As it is having 3 number of flip-flops, number of states which can be produced by this counter is equal to 8. So it can count up to your 8 clock pulses in this 3-bit triple counter or asynchronous counter. So as like here in your 2-bit counter up count sequence. So now we have, when you are observing the score difference between your successive states, which is equal to logical 1, so which is a plus 1, so hence it becomes the up count sequence. As here triple counter we need to design, so we have to prefer the toggle state, or if you use the JK flip-flop, it has to be function in your toggle mode. So toggle mode in your JK flip-flop you can obtain when J and K are equal to logical 1. Hence we connected J and K of 3 flip-flops so to your high state. So J become logical 1 as well as K is also equal to logical 1. So now here in your triple counter designing, so we have to do that. The connection of this is your first flip-flop is your least significant bit of your counter, and the third flip-flop now it is acting like your most significant bit of your counter. So now the third flip-flop will be the most significant one, and second flip-flop is your second flip-flop will be the counter which is in between the least significant and your most significant bit. So now, so whenever we apply a clock signal here, so now these are operated with a negative edge trigger. So initially using asynchronous counter, sorry, asynchronous input. So we are going to clear the contents of your all the flip-flops. So all will give you the initial state which is equal to logical 0. So hence QA is here we have taken it with the QA is equal to least significant bit and QC is equal to the most significant bit. Now using a clear input, let me reset all the states of your flip-flops, these 3 flip-flop states with the 0 state. Now upon your falling edge of your first clock pulse, which is connected on your QA, so QA will transfer its state from present state of 0 to the toggle state of logical 1, and this one is continued till you get your next clock pulse. So for every clock edge of your given clock pulse, your least significant flip-flop will toggle its state. So now second clock pulse, now it turn back into the logical 0, and third clock pulse it will turn into the fourth, this logical 1, fourth clock pulse negative edge, so it comes back to its 0. So next fifth clock pulse it will move to your logical 1, and sixth clock edge, so again it comes back to 0. Since my previous state is 1, so JK inputs are 1, 1. So upon giving the negative edge, so it has to come to the logical 0. So in the same manner, this logical 0 is continued till you get your next negative edge on your clock pulse. So next edge negative on your 7th clock pulse, so your output of your QA is toggle to the logical 1, and your 8th clock pulse, so your output of your QA is significant bit flip-flop is toggle to 0 state. Now, so this QA negative edge of your QA is acting like a clock for the second flip-flop, and QB negative edge is acting like a clock for the third flip-flop. So are the most significant flip-flop. Since that, so till that negative edge, so though your T input is logical 1, so we are not obtained any negative edge, which can the control signal is not enabled. So hence the second flip-flop will maintain the previous state of your 0 for the first 2 clock pulses. Next, upon getting that QA is a falling edge on your clock of your second flip-flop, this will alter the state from 0 to 1 since the JK inputs JB and KB are equal to logical 1, and this logical 1 again it is continued till you get your next negative clock edge of your least significant bit. So now on this negative edge of your second negative edge of your least significant flip-flop, QB will alter from 1 to 0. The same manner, this 0 is continued till I get the negative edge on your QA. So then it will shift it to the logical 1 state. The same manner, so QC will toggle its state upon getting the clock edge on your second flip-flop, which is on QB. So till that, so it will maintain the initial state, which is 0, though it is T input is 1. So T input is 1, but we didn't get your negative edge on your clock of your second flip-flop, since second flip-flop output is acting like a clock to the third flip-flop. Next, upon getting that negative edge, so your state of the last flip-flop, which is the most significant flip-flop, will alter with a logical 1 state. Now, already we discussed this as your triple counter, because here the clock frequency is on your first flip-flop, which is least significant, is divided by 2. On your second flip-flop, the frequency is now it is divided by 4, and in your third flip-flop, your frequency is divided by 8. So hence we obtain only one clock cycle for 8 clock by only one clock cycle on your last significant bit or the most significant bit after 8 clock pulses. So you can complete only one cycle on your most significant bit. Now by observing this stage, so initial state is 0. Upon your negative edge of your second clock, your state of your QC, QB and your QA is 001. Next 00010 on third clock pulse. Next 011 on your fourth clock pulse, and 100 on your fifth clock pulse, 101 on your fifth clock pulse, and 110 on your sixth clock pulse, 111 on your seventh clock pulse. And when we comes to your eighth clock pulse, your state of the flip-flop, since it is stopped with all the 3 ones, so it will all will be reset to the 0 state, and again the sequence of your up counting is repeated from that 9th clock pulse to the 13th clock pulse. Okay, at your 16th clock pulse, again it comes back to its initial state, which is 0 0. So this is about our up counting. Next, down counter design. So like in the 2-bit down counter, here also we are going to connect your JK inputs to logical 1 state. Common clock is U. So here we are going to apply the clock signal on your first flip-flop, which is the least significant bit, and least significant bit complemented output is applied to the second flip-flop clock. So the second flip-flop complemented output is connected to the third flip-flop clock signal, and JK inputs are logical high. So initially we are going to reset your flip-flop. So QA bar become the clock for it is acting like a clock to the second flip-flop. QB bar is acting like a clock for the third flip-flop. Now hence we included here along with the QA the output of your first least significant bit. So we also indicated or we also represented in a timing diagram with complemented state of your least significant bit and your second flip-flop uncomplemented state as well as the complemented state. So now for every negative edge of your clock on your QA, your output will toggle from 0 to 1 or 1 to 0. So like this we will get on your QA. Exactly QA bar is complement of your QA. So we have drawn that too. So now QB is dependent on your QA bar negative edge. So till that negative edge, so previous state is 0, Next state will now it is altered to logical one, and this one is continue till you get your negative edge on your complementary state of least significant bit. So hence at that state of your second clock edge, negative edge on your QA bar, your output of your QB is shifted from 1 to 0, and this continue till we have your negative next third negative edge on your QA bar, so it will shift from 0 to 1. So QB bar also we have calculated here, so in order to obtain your output of your third flip-flop. So initially your QC is 0 because of this QB is going into negative edge. So QC, where it is QB is acting like clock for your C flip-flop, and with JK inputs are 1 1, hence it has to toggle its previous state from 0 to 1. So this one is continued till you get your next negative edge on your second flip-flop output. So at this instant, upon fifth clock pulse, we got your negative edge. So there, so your output of your QC will toggle from 1 to 0. So now if I am going to count here from your QC, QB, QA, where QA is the least significant bit, QA is the least significant bit here, and QC is the most significant bit. So like this if I write it, so QA is 0, QB is 0, QC 0. Whereas here QA is 1, QB is 1, and QC is 1. So next state after 0 is 7. After 7 it is of 6. 6 after this we have 5, then we have 4, then we have your 3, we have your 3. So 0, 1, 1. So 0, 1 on your QB, 1 on your QA. So 3, next 0, 1, 0, which is 2. QC is 0, QB is 1, QA is also 0. Next. So after 8th clock pulse, again the count sequence is repeated from your initial state of 0. So it counts your number of states in a down sequence. So hence it comes under as a 3-bit asynchronous or your ripple counter. The next class we're going to design the 2-bit synchronous counter. Thank you.